Welcome everyone to today's Google Cloud webinar series. The topic today is troubleshoot common GKE challenges on Google Cloud. GKE, or Google Kubernetes Engine, is a powerful platform for containerized applications. However, its flexibility and complexity can sometimes lead to challenges for developers and SREs. In this live session, we will guide you through a strategic approach to identify and mitigate some of the most common GKE issues. You will learn about 3 typical types of GKE issues, and you will also establish a systematic approach to identifying and mitigating common GKE issues. Here's the agenda for today. We will start with a very brief introduction to GKE and GKE troubleshooting basic principles. Then Rochelle, my colleague in GCP support, will present 3 typical and common GKE issues and demonstrate how a GKE specialist in Google would identify and fix these issues. The 3 scenarios are pause crash looping, pause unschedulable, and nodes not scaling up. We will also have time to answer some pre-submitted questions and live questions. If you have a question to ask, please put it in the live chat, and we will come back to answer some of the questions at the end of the webinar. So let's have a very quick round of self-introductions. I will hand it over to you, Rochelle.
Thank you, Dave. Hello, everyone. I am Rochelle. I am working as a technical solutions specialist and supporting GCP Premium Cloud Support customers. It's been more than a year since I have been working with Google on GCP, and I am based out of India. In my previous role, I have extensive working experience with Linux, networking, and infrastructure storage related problems, and also on the cloud platforms. Previously, I was working with telecom domain, and I was working as a project engineer there. Thanks, Davi.
Hey, thank you very much, Rochelle. So let me introduce myself. I'm a Google Cloud TAM, or a technical account manager located in Singapore. I've been working at Google for 3 years. As a TAM, I support some of the biggest Google Cloud customers in Southeast Asia. I help customer IT and developer teams with solution engineering, capacity planning, change management, training, support, and many other things. Before my current role, I used to work as a game developer, a network engineer, and a security engineer. Okay, before we jump into today's scenarios, let's quickly cover the methodologies of GKE troubleshooting. First, some basics. Kubernetes is a popular container orchestration system, and Google Kubernetes Engine, or GKE, is the most scalable and fully automated Kubernetes services in the market. If you're new to Kubernetes or GKE, or if you want to know why GKE can be better than other managed Kubernetes services, or running your own Kubernetes clusters, here are some quick videos to get you started. Kubernetes is very flexible, but it can also be very complex. Problems can occur for many different reasons, including misconfigurations, software bugs, node failures, among others. The good news is that GKE has comprehensive monitoring features that can help you isolate the issue. And in a few minutes, Rochelle will show how you can navigate these monitoring tools. For troubleshooting a complex system like Kubernetes, locating where the problem is can be more difficult than addressing the problem. That's why we recommend taking a systematic approach to troubleshooting GKE issues. The first step is to identify and describe the problem. Next is to gather information about the problem, among which one of the most important steps is to find the error message or configurations that can reveal the root cause of the issue. Once we know the root cause, we should carefully develop a solution that has a clear execution steps and rollback plan with user impact in mind. It is also advisable to get help from whatever resources that are available to you, including Google Cloud support and the community. Here are a few things that can make your GKE troubleshooting much easier. One is to enable logging and monitoring. You should make sure workload logging and system monitoring is enabled. You should learn to use the Metrics Explorer and Log Explorer to inspect logs and metrics. You can also consider enabling control plane component logging to inspect logs of Kube scheduler, controller manager, and Kube API server. Take note that logging may have a cost, and certain issues can create a high volume of logs in a short time. So consider configuring a budget so you can get notifications when your logging cost increases. Step 2 is to check the GKE troubleshooting guide to fix some of the most common GKE issues. The guide has more than 20 types of issues documented and can be very handy when issues occur. Last but not least, get help from Google Cloud Support, from the community, from your Google team and customer engineers, from the Kubernetes gurus in your company. Use all the resources you have to move things forward. This is especially important for complex issues or issues that involve multiple parties. Okay, that's enough talking for today. Let me hand over to Rochelle to demonstrate how to troubleshoot some of the most common GKE issues. Over to you, Rochelle.
Thank you, Dave. Hello, everyone, again. So we are going to explore three of the most common GKE challenges that are faced by customers. The first one that we are going to talk about is pods are in crash looping state. Basically, when this scenarios occur, you can see in your workloads tab that the pods or the deployments are in the crash loop back of stated, and you will also see a banner which will portray the same. We will look at some of the most common scenarios and then move on to the demonstration of one of the scenarios where crash loop back of error occurs, and we will try to fix it. So the possible reasons for pods getting into crash loop back of state is, as the names suggest, container running inside the pods, they crash for various reasons, and Kubernetes component container runtime notices that and tries to restart the application in the hope that it starts again and starts serving the workload. There are many reasons for container that crashes, basically due to application errors, out of memory kill, and liveness probe failures. These are the three major categories due to which pods crash loop. The most common out of these three is application error. Now, this application error is reported by the container itself, and it happens when container's main process exits due to various issues like configuration issues, file system permission issue, connection issues if application depends on any other services, for example database, to connect to and get the credential or get the database in memory. Just a quote of example. Another one popular reason for crash looping is out of memory killed. Whenever a container is provided with memory request and memory limit, it cannot use the more than memory which is allocated to it in the memory limit. So when containers tries to obtain more memory than defined in the limit, the container runtime starts to crash loop and kill it. And this happens again and again, and which uh, results in a crash looping situation. The third and less common scenario is liveness probe failure. Many customers or many users configure liveness probe to ensure that application workloads are in healthy state, and that's one of the recommended practice to configure liveness probe. However, sometimes liveness probe endpoints, they do not respond, and that's the reason why container runtime thinks that the application is not responsive, it is not alive, and it kills the container running inside the pod. This starts a process where container starts crash looping until the response is positive. So these are the main three reasons why a pod would crash loop. Now we will go on to a demonstration where we will see one of the application related issue and how do we isolate that issue. Demo, we are going to explore one of the commonly seen occurrence with the Kubernetes workload, which is crash loopback of error. Here in my cluster, I have GKE Playground project, and I have multiple clusters in this project. Let's see all the clusters. Some of these clusters I have pre-configured and others are Anthos or AWS registered clusters. Let's see the workloads, and as you can see, there are certain workloads which are already in not available state or not in ready state. Two of the workloads are in crash loop back off, and the type of these workloads are pod, and the third workload is type of deployment. Let's see if we can check how many pods are there inside this deployment. It says the deployment was created quite a while ago, and so far there has been 10 restarts on each 3 of the pods containing in this deployment. And if you see the observability graphs, we are seeing the dotted lines, which means the pod is not continuously utilizing the disk memory and CPU resources. Here on the banner we can see the pod errors saying crash loop back off. Let's explore this further. It says that Ubuntu keeps crashing because it cannot restart. It cannot continuously run some of the containers and they keep restarting, and the source of these errors are coming from all 3 pods inside this deployment. And there is a recommendation to view an interactive playbook. These interactive playbooks are where users can directly interact and figure out the reasons why a certain workload is not functioning as expected. Okay, so when you click on this interactive playbook, there is a troubleshooting guide that opens up on the left hand side, and this is entirely new design customized just for the troubleshooting playbook. The first step to troubleshooting is viewing which containers are restarting. So we are seeing that Ubuntu and Nginx containers, they are restarting very frequently, and this restarts of workloads are per 5 minutes interval. The next step is to figure out the causes of crash loop back of errors. So what really causes the crash looping is there are multiple reasons behind pods getting crash looped. One of the most commonly observed cause is application itself. The container that runs inside the pod, it exits itself, and when the container exits, it reports some errors, and Kubernetes tries to restart it. So if you see the application logs, we have sleep command. We have tried to run the sleep command, but if you can observe closely, there's a typo in the command, so that's why it's exiting with an error, and that's why Kubernetes tries to restart it every time it exits. So this is basically how you can identify if there is an application level issue and the pod is restarting due to application side of errors. There can be other errors as well, which will cause this which will cause the containers to basically exit. They are for example, if the command inside the container tries to access a file which it doesn't have any permission to, for example a root file, or there is any configuration issue within the image itself, then also the container keeps restarting. Here we can see the short-lived containers. They are Nginx and Ubuntu. For Nginx also we can see some errors. No permission to list a ingress class. because the default service account does not have ingress class in the API group. So this is one of the compatibility issue with the Nginx controller. That's why it is restarting very frequently, and that's what you see in the next section. Here the next section shows you the pods that were terminated due to application errors. Basically, these are the logs, these are the audit logs printed by the GKE cluster, and it reports all the pods that were deleted by node service account. This is the principal email information for this particular action. So all these pods were deleted by their node service agent. So what are the next steps? The next step for the crashing pods depends on why the pod is basically crashing. In this example, the pod is crashing due to the misconfiguration, but there can be other issues as well, such as missing config map, environment variables, or missing command line arguments. The pods can also crash loop due to out of memory. For example, there is a memory request and memory limit configured on a particular deployment, so that if a pod tries to acquire more memory than it is allowed to, then the memory limit, then the node basically tries to kill it, and that results in out of memory behavior. So if those behavior is explored, then it can be observed here. All these sections, they contain such behavior where out of memory killing is happening due to the node. There is another reason why the pods crash loop, which is liveness probe failure. So liveness probe failures are basically the probes that are used to determine if the container inside the pod is healthy, and that's the reason why they are executed at frequent certain interval. And if they continuously keeps reporting a negative response or invalid response, then Kubernetes assumes that the application is not responding and reports the liveness probe failures. Upon the liveness probe failure, as per the configuration, Kubernetes tries to restart the pod, and if after the restart also the application does not respond, the liveness probe does not succeed, the pod will keep restarting, and that will result in crash looping situation. So those are the main reasons. Identify the application errors, investigate the out of memory issues, and investigate the liveness probe failures to investigate why the pods are crash looping basically. The next section is correlation of the change event. Here all the events that are executed by any users are explained. So for example, a user has change the image of a particular deployment at certain point of time, and that's when the crash looping starts. We can correlate it from the section easily. For future mitigation, if any pods keep restarting, we can easily create an alert so that users can be sufficient users can be notified via alert. Okay, so now we have identified what is causing the issue, which is basically an incorrect command in the pod or deployment manifest. Let's try and fix it. We'll go to the Kubernetes workload section where we have configured our deployment Ubuntu, and we'll try to edit and fix the typo that we made. We'll click on edit on the deployment page. It will take us to the YAML section, and let's try and find the typo in the argument section. Here it is. So we have incorrect sleep command.
However, there is one more issue here. We have sleep command, but it needs an value, an operand, just like the first sleep command. We haven't provided any. So let's add an operand of 1 second. So basically this will tell the container to sleep for 10 seconds, then log that sleep is expired and again sleep for 1 more second. Let's save this. Okay, there's a pending update. After forcing a new update, all the deployment pods are in running status. Let's see if we see any logs. We are just seeing the sleep expired log that this container is printing. All the errors have stopped coming. Yeah, so that's the demo of how we fix the pods which are crash looping.
So let's move on to our next demo, which covers a scenario where pods are unschedulable due to various reasons. Whenever there is an issue where pods are unschedulable, you will see that error message in the banner itself, like it's shown in the screen here. If you can click on the cluster and then observe on the workload page, there also you can see if the pod is unschedulable. And there are certain steps and there are certain reasons why the pod would be unschedulable, and we'll explore what are the reasons why a pod would be unschedulable. There are various reasons which include insufficient resources in the cluster. Let's say a pod requires resources like memory or CPU, which is higher than the machine type that is selected for the cluster. A pod requesting 50 vCPU, but the machine type in the node pool is only restricted to 16 vCPU, then it would be in unschedulable state. Another one is node selector. When the pod manifest or deployment manifest mentions any node selector for a particular type of node or machine family, and that does not exist in the cluster, then also the pod can remain unschedulable. Or there's one more reason to it. If that machine type or family exists already in the cluster, but it doesn't have any freeable resources or any resources where pod can be accommodated, then also it will be in unscheduled state. The third one is the tolerations. Let's say there is a toleration added in the pod, and there is no there is a taint added in the deployment manifest, and that the node doesn't tolerate. That also can lead to a situation like this. The next one is very corner case, which is the pod topology spread constraint. We will explore this in the demonstration as well. Pod topology spread constraint is basically used to ensure that Kubernetes workloads are highly available across nodes or across multiple zones. And it basically ensure that equal number of replicas of the workload are spread over multiple zones. And if the condition mentioned in the pod topology spread constraint are not met, then also pod can remain unschedulable. Uh, the one more common reason for pods not being scheduled is if the maximum pod per node limit is reached by all the pods in the cluster, then there is simply no space for the pods to be scheduled unless the cluster is scaled up with additional nodes or additional node pool. In the next step, we'll try to look at a couple of scenarios which results in pods being unschedulable and how to triage them and how to fix them.
Now we will look at the cluster, and in this cluster we have some pods which are unschedulable, and basically Kube scheduler is not able to schedule them on the GKE nodes, and we'll try to troubleshoot them. If you look at the cluster, this is a cluster that we are using, a regional cluster in US Central 1, and it complains about pods being unscheduled already. Let's go to the workload tab, and we have already filtered cluster regional and all the workloads under all the namespaces except the kube system namespace, which are in running or pending state. And we can see there are two workloads which are of type deployment, and they don't have minimum availability. So let's start with the first one, which is Nginx deployment. We'll look at the second one later. The first one complains about pod errors, and pod errors indicate the pods are unschedulable. If we click on show details, it shows insufficient CPU. This is self-explanatory. We need to check how much CPU these pods are requesting. Let's click on one of this pod, and let's look at the amount of resources this pod is requested. So on clicking the container, we can see the CPU resources requested is 500. Now if you look at this figure closely, it's 500 cores, not the 500 millicores. It seems like a typo, because workloads generally don't need that much CPU. So what I'll do is I'll edit this deployment manifest where this pod belongs. Here we are on the deployment page. I'll just click edit, scroll through the portion where the CPU is mentioned. Instead of 500, I will choose 50 millicore, which is a fairly generous amount of CPU for our existing pods. All the resources get updated, and as per the rolling restart, the fresh replicas of new pods are already being created. So that means they are already scheduled somewhere. So scheduling problem has been resolved, and there you go. We have all three replicas of Nginx deployment pod running here. Now let's look at the second deployment, which was in pending state. We have this deployment called topology test, which also complains about pod errors, pods being unschedulable. And if we look at the pod count, there are 5 pods, and only 2 out of 5 are unschedulable. Remaining 3 are schedulable. So let's click on show details. In the show details, we see the reasons why the remaining 2 pods are not scheduled. They did not, and none of the nodes matched pod topology spread constraint. So again, we'll need to look at the definition of this deployment, where the pod topology constraint is defined. So we are again at the deployment YAML, and scrolling through the specification of this manifest, we can see that there is a topology constraint defined, and the max queue is defined as 1. This means that the maximum skew that this deployment can tolerate is 1. For example, there are 3 zones in a particular GKE cluster, and out of these 3 cluster, no 2 zones can have more imbalance in the number of pods more than 1. So if one particular zone is having 4 pods, the remaining 2 can have 3 pods or 5 pods. The difference between these number of replicas cannot cross 1. So that's what defines port topology constraint. And the port topology constraint is majorly used in the Kubernetes workload, so that the replicas of the pods are spread equally, or more the distribution is more uniform across multiple zones in case of zonal cluster. We already have three zones in this regional cluster. I can show you default node zones are B, C and F, so that should be okay. 5 replicas should be able to schedule on B, C and F zones with max queue of 1. Then why it is not being able to schedule? So let's look at the definition again. There's one parameter called minimum domains. So this minimum domain defines the value of the number of zone that the workload should look in the cluster. Now we just saw that there are only 3 zones defined in this GKE cluster. So Kubernetes assumes that there are 10 zones and it is looking for the next 2 zones to schedule the pending workloads, which is never going to happen. That's the reason why it is unscheduled still. What we can do is we can change the minimum domains to 3 to match the actual number. Click save, which should trigger a rolling restart of this deployment, and let's see if the pods get scheduled. There you go, all 5 pods are in running state now. Since we instructed Kubernetes that there are only 3 domains, that means there are only 3 zones in this autopilot cluster or in this regional cluster, so that all the pods are scheduled with max queue of 1. Okay, so all the deployments and all the pods have been scheduled. Apart from CPU and memory and port topology constraint, there can be multiple reasons why the pods can remain unscheduled. Majorly, Kube scheduler's task is to schedule a pod based on the resource request, anti-affinity, affinity rules, topology constraint, and CPU, GPU, any additional disk request. All the resource request gets considered by Kube scheduler when looking for the node match for that particular pod, and that's how the matching happens. If none of the node matches the criteria, Kube scheduler triggers scale up via cluster autoscaler and scales new nodes, which again are able to schedule these pods.
Okay, so that was the demo regarding the pods being unschedulable, and as you might have observed, pod topology constraint have many corner cases, and there are some complex situation which may trigger the pods to remain unschedulable, even though there are resources and autoscaler is able to scale up a new node pool to basically schedule them. Moving on to our next section, there is a third scenario which is very common while working with GKE cluster, which is cluster nodes not able to scale up. This kind of issue appears in the cluster banner under the Kubernetes cluster page, and the warning message says scaling issues on the console itself. There are various reasons why a scaling up issue would occur. Uh, uh, some of the common reasons are maximum number of pods limit has reached. In cluster auto scaling configuration, you can define maximum number of nodes to which cluster can be auto scaled and scaled up to. If that limit has reached, then the cluster won't be able to scale up. There is also a project-wide quota for CPU, memory, GPU, and SSD resources. And this quota applies to managed nodes and managed instances as well, along with compute engine and other managed services instance. So please have a watch on the quota limit for the resources depending on the node pool that you are using. The third one is IP space exhausted. There are two kinds of IP address in the VPC native GKE cluster. One is primary IP address range, which is used by the nodes themselves to allocate the nodes IP addresses in the node pool. And another one is the secondary range, which node itself assumes one entire range, network range, which it can allocate to the all the pods which reside and schedule on the particular node. If the IP address space, which basically you define it when creating a cluster, is exhausted, then also scale up may not be possible. The fourth reason is node auto provisioning limit exceeds at the cluster level. This is a GKE specific feature which enables users to fork an entirely new node pool if the existing node pool does not cater to the requirement of the workload manifest. For example, the workload requires a particular number of particular resources, like more CPU resources than defined in the default node pool. Then node pool auto provisioning can fork entirely new node pool to match the specification mentioned in the deployment manifest and create new nodes to schedule that particular workload, and it will schedule that. So this node auto provisioning setting has a limit reaching which you won't be able to scale up even the existing node pools, which are default node pools. The last situation is unhealthy cluster. If more than 45% of the nodes in the cluster are unhealthy or in not ready state, autoscaler will stop all the operation, including scale up, scale down, and all the operations, because the cluster is not healthy. In the next slide, we will look at the demonstration of one of the commonly observed scenario while which is faced by users when scaling up their node pools in the cluster. Demo, we are going to look at some of the scenarios where node pool scale up or node scale up is basically stalled and errors out due to various reasons explained previously. Here we have a cluster called cluster autoscale, and it is running on the version 1.27.3, which has a total size of 4 nodes. If you can see in the nodes tab, we have a default node pool which has 4 existing nodes and configured with minimum 1 node and maximum 10 nodes with autoscaling enabled, and it already has 4 nodes in this cluster. If we look at the workloads, then this cluster only has one workload, which is called Nginx scaled, and it's running with one replica. Now let's try to observe the configuration of this deployment. We have designed this deployment in such a manner that anti-affinity rules can be applied, and pod replica of this deployment can be spread across multiple hosts, and no two replicas can be scheduled on the same node. This is achieved by anti-affinity rule. Now let's try to scale up this workload. So I have scaled up the replicas, and all 3 replicas have started. Just the remaining 2 replicas have been started already, and if I refresh this page, I can see them. The second replica is scheduled on another node, which is not the same as the first node, and the third replica, that's also scheduled on a separate node. So basically the replicas are distributed across 3 out of 4 nodes present in the existing node pool. Now let's try and scale the replica count of 5, which means that the fourth replica should be scaled up or scheduled to the fourth remaining node, and we will not have any nodes available for scheduling the fifth replica. Let's see this in action. Yeah, as expected, we are able to see the fourth replica is already in running state and is assigned fourth node, but the fifth replica, yeah, this one is unschedulable. Moving on to the events tab, it says 0 out of 4 nodes are available, and none of these nodes are matching the pod anti-affinity rules, which is as expected. In such a situation, the pending pod or unschedulable pod should trigger a scale up event, which should be able to scale up a new node, and we already see that it's happening. Let's wait for a while till the new node is scaled up and this pod is scheduled. If we refresh the events tab, we can see that there is a message with the reason failed scale up, and the message says the node scale up in US Central 1C associated with this pod is failed due to IP space exhausted. Now we are not sure what exactly this means, so let's try to revisit this error. So we can see that cluster has already started creation of new node pool, which is forked by node auto provisioning feature that we have enabled on this cluster, which will try to create a new node pool and schedule one node where this pod can be scheduled. We can see that it's still using the same custom pod IP address range that is being used by the default node pool, and trying to update the instance group to have one instance at least. If we go to the error section here, we can see the IP space exhausted message, and in the error message we can clearly say that IP space of this particular subnet is exhausted. Now let's look at this particular subnet. We are using a custom VPC subnet for this cluster, and here we have only one secondary IP address range, which is /22, and according to this table, this particular CIDR can accommodate only 4 nodes, and we already have 4 nodes in the default node pool. That's why the newly provisioned node pool is not able to scale up one node as required. So what can we do to overcome this situation? There are basically 3 options which we can try to mitigate the situation. One of the most convenient and popular choice is to make use of discontinuous multi-pod CIDR. This option is available after in the recent Kubernetes releases with the GKE. With this option we can add additional subnet for the secondary pod IP address range and allocate that range to the cluster. Another options are basically creating a replacement cluster and planning it the better. One more option is to create a new node pool with a smaller number of maximum pod per node. If we keep the number of pods per node smaller, it will need a smaller subnet per node, and you can basically have more nodes. This can be calculated with the calculation provided here in this document. I have pasted the link to this document in the chat. So we will try to mitigate this situation by creating an additional subnet in the secondary IPv4 range. So let me click edit and create another range called custom pod 2. I can provide any range which is not utilized. Cool. So we have the immediate next CIDR range after the previous CIDR finishes, and it is identical to the previous one. I'll click save just so that we can have this subnet added in this custom VPC. Okay, this has been added. However, still the cluster does not know that we have added this particular secondary IPv4 range. So we have to add the same in the cluster configuration page as well. This is where the setting is on the cluster main page under the networking section. There is an option to provide additional pod IPv4 ranges. Okay, we can see the additional pod ranges populating here, and we can choose the same, click OK, click save changes. This will take a while. It seems the operation has been completed. Now let's see to the pod which is unschedulable. The pod has triggered the scale up again, and the failed scheduling and failed scale up messages haven't been seen for quite some time. Let's try to refresh this page. Okay, after the refresh, the pod has been assigned to this newly created node from the node pool, and now we can see that this has been scheduled. And if we go back to the workload section, we can see all 5 pods are allocated. Going by the size of the CIDR range that we added, which is /22, we can add probably 3 more nodes and add 3 more replicas of our Nginx scaled workload. So this is how we can mitigate this issue, by adding a secondary IPv4 address range, especially for pods in the existing VPC network.
Okay, thank you, Rochelle, for the excellent demo on the GKE troubleshooting scenarios. Now let's come to the Q&A session. First, we will start with some of the pre-submitted questions. Then we will take a few questions from the live audience. The first pre-submitted question is how to filter exact error messages in operation suite or stack driver logs. So for simple queries, you can go to Log Explorer and start with some of the example queries in the documentation. However, if you want to configure specific filters, especially if you want to configure alerts based on error messages, you will need to learn the logging query language. So here in the screenshot is an example query that matches all error messages that contain the word failed in the text payload in all Kubernetes container resources US East 1 region. You can make it even more complex, but as if you have a specific filter that you want to configure, you will need to learn the grammar first. Okay, so the next question is how to identify services using deprecated Kubernetes APIs. We all know that Kubernetes APIs are quickly evolving, and the old APIs are often deprecated and eventually removed. Here are a few steps that you can take to stay ahead of API deprecations. First is to understand the Kubernetes API deprecation plan, which is usually released in the official Kubernetes website and GKE website. Second is to read deprecation recommendations in the JCP console, which is shown in the screenshot here. It usually contains important information such as the user agent that calls the deprecated APIs. Next, if the user agent is internal to your GKE cluster, usually it is not so difficult to locate the agent and upgrade them to higher versions, or you can update the code to call the supported APIs. Things may get a little bit more complicated when external agents are calling the deprecated APIs. In that case, besides the user agent names, you can find the source IPs and other useful information in cloud monitoring logs. Last but not least, if a mandatory GKE version update is coming, but you're still not sure about the impact of upgrading the APIs, please contact GCP support or your TAM to get help. Okay, the next question is it possible to deploy to GKE cluster without YAML and just command line? The answer is most likely yes, but depending on the situation, using just the command line might not be the best practice. If the purpose is to migrate from another service such as Cloud Run to GKE, actually there are multiple migration options available. You can migrate to services, deployments, horizontal pod autoscalers, and you need to consider which option is the best for you. For complex deployments, YAML file is generally easier to read and easier to troubleshoot. A 100-line YAML file is easier to manage than a 30-line kubectl or gcloud command. Also, if you want to implement infra as code solutions or migrate workload to a different cloud provider, it is usually much easier with YAML files. Okay, so these are the pre-submitted questions. Now we will pick a few questions from the live chat. I will hand over to Rochelle to pick a few questions from the audience. Hi, Rochelle.
Yeah, so the first question is from Dheeraj. Does nodes not scaling down also fall in the same category as node scaling up? The answer to this question is yes and no. Basically, both scaling up and scaling down operations are handled by a cluster autoscaler component of GKE. However, conditions for scaling up and scaling down are totally different. For scaling down the nodes, a cluster autoscaler considers multiple options, such as the conditions needs to be favorable for downscaling the via autoscaler. If pods are able to be scheduled on other nodes which are underutilized, then the node pool can be scaled down while evicting the system pods running on the existing nodes. We will move on to the next question. This question is from Raja Seelan. GKE pod multi-sider ranges. Can we remove assigned pod siders? The answer to this question is yes, but there is one condition. By multi-pod sider ranges, I am assuming that you are asking about the pod subnet secondary IP address range, which is added apart from the primary address range configured while creating the cluster. So the answer to answer your question, it is possible, but you have to make sure that the secondary IP v4 pod secondary range is not currently utilized by any of the node pools. If it is not currently utilized, you can go to the cluster console page, as I have showed in the third demo of node scale up demonstration. You can click on additional pod IPv4 range and deselect the selected secondary range from there, and click on save. That will update the cluster and free up the multi-pod CIDR range being used from that cluster. I will hand it over to Dave for the next question.
Thank you, Rochelle. Next question is that is there any dual AI feature that can help to troubleshoot GKE issues besides the dual AI explain logs feature? The answer is yes. But to use that feature, you have to use a product called error reporting. I'm putting the documentation on error reporting here in the chat. So basically, if you go to this link, you will know that you can actually configure multiple environments to automatically report error data to error reporting. And the source of the errors can include Google Kubernetes Engine. You can also configure Compute Engine, Cloud Run, Cloud Functions, and many other different services to send the errors to error reporting. So with Dual AI, you're able to troubleshoot errors in the error reporting tool. So I'm now sending another link in the chat. So if you go to that link, you will see that you can actually ask Dual AI to interpret an error, and this error can be a GKE error. So this is how you can use Dual AI to troubleshoot errors from GKE. Also, you can use the generative AI options like BART to analyze whether your GKE configuration YAML files have any issues. So actually, you have many options to use Gen AI, Dual AI to help you with your GKE deployment. And the services and products are actually improving every day. So we would expect that more features will be available, and it is going to be even easier for you to troubleshoot GKE issues. All right. I think due to time constraints, we cannot really answer all the questions today. I see many other questions submitted. Some of them, if it is relevant to this session, after this webinar, we will try to answer them in the comments. But for some others, that may not be so relevant, or it might be too complex for us to answer. The recommendation is that please, if you have a GCP support, please reach out to the support team, or you can ask the question to the community so that you can get your questions answered. All right. Before we wrap up the session, I would like to thank everyone for your participation today. Here are some additional resources for you. Please use the link here to share your feedback for today's session. And we have a few other upcoming sessions. If you're interested, please register for our upcoming Google Cloud webinars and events. And also, please join the Google Cloud community and engage with Google employees and other customers of Google Cloud on technical discussions. Thank you very much. So by that, I think we will end the session today. Thank you, everyone, again, for participating in today's session. Thank you.
Thank you.
Bye-bye.